So we are after lunch. Those of you that know me probably know that I like to do very technical, deep dive presentations. So I hope everyone has got their coffee. And now we are going to deep dive into MSTP on MikroTik. So a little bit about me. Who am I? I'm Thomas. I'm the team lead at Unimus. I've been a network and admin architect for a long time. My real passion is in automation and monitoring. I'm an ex-MikroTik trainer and consultant. Sadly, I don't just have enough time in my day anymore to train, although I miss it really a lot. A little bit about Unimus. We are a network automation and configuration management system, blah, blah, blah. If you like to talk to me about Unimus, we have a booth down there in the exhibitor area. Come around and talk. I'll be happy to show you what we do. So, without further ado, yes. This is not for you. A lot of my presentations find their way on the internet as PDFs, and there is a lot of context missing, so since you are here, this does not apply to you. All right, so let's get on the topic then. So why do we even care about MSTP? Well, I really feel like MSTP is one of those misunderstood and often frowned upon protocols, and therefore it gets not deployed a lot, and I feel people are missing out on a cool piece of technology in their networking toolkit. And yeah, it has real use cases, and it solves many architectural challenges in complex networks. And hopefully by this presentation, you will understand a little bit about it and understand that it's not a scary protocol, it's a protocol that's well worth knowing and deploying in your network. So we are going to look at a network like this. This is actually inspired by a real network that I did many years ago, and this was a hospital network. So it was a big hospital, and this is just a network inspired by it, although in topology, it's very similar to what was in there. So we can actually see that we have a few logical areas here in this network. So we have some clusters of servers down here. And so actually it's very common, at least in this part of the world, that in hospitals you have many clusters of servers because each specific technology, like radiology department will have their own cluster with their own services, microbiology and immunology departments will have their own software and own clusters. So there are clusters of servers in here, and then there is, here floors inside of the hospital. Here we have just one switch and one access point for one floor. Of course, that would be more complex in a real network, but it's just an example when on each floor you have a switch, then you have some PCs where doctors and nurses connect to, and then you have an access point which has like a public Wi-Fi for the people there to use. So as you can see, this is a highly redundant network, as hopefully in critical infrastructure like hospitals you would have. So you don't want to have any single point of failure in a topology like this. And so we can see here that we have a very highly redundant network because we want to avoid those single points of failures. Literally, lives could be on the line if something fails. All right, so we are going to talk about topology like this. And so before we dive into it, though, let's start with a little bit of a STP primer, a little bit of an intro to spanning tree. So spanning tree protocol is a core protocol in the Ethernet network suite, and its job is to ensure path-free topology by blocking redundant links in the topology to achieve a network without loops. By its definition, though, due to line blocking, STP actually decreases the available links in the network because it blocks those redundant paths to achieve a loop-free topology. So that's definitely a downside. And another downside historically was that spanning tree struggles with large network topologies. As soon as you get into maybe like 50 plus, 100 plus switches or bridges, to be more exact, STP can have issues. Original STP. We are talking here about the STP protocol which was designed in the early 90s. So how does an STP actually work? Well, in principle, it's quite simple. The spanning tree selects a root bridge, so which these days is usually a switch, and calculates a non-looping topology for the network. And so how this is done is that all bridges or switches calculate the shortest path to the root bridge, and then all other links between the bridges are disabled. So yes, we get a loop-free network, but like we mentioned, all the redundant paths become unutilized and blocked. So let's see it at work. We have this nice, lovely network. We see it wouldn't work without some kind of a loop prevention system. So what would STP do in this network? Well, before that, let's explain a bit more about this network topology, so we understand what we are doing with it, and then we can look at the STP result. So we have some WAN area here, so we see we have redundant internet connections. For the purpose of this talk, we don't care about that. We have some backbone, which connects our edge switches, VPN access concentrators, and our inner routers, which actually terminate all of the subnets. For the purpose of this talk, we don't much care about that either. Then, like we mentioned, we have multiple server clusters. So we have server cluster number 1 here, server cluster number 2 down here. And then we have our internal LAN. Like I mentioned, this is for the doctors and nurses, et cetera, et cetera. And then we have a guest Wi-Fi network, or a network for people who are staying in the hospital to have internet connectivity to. And we can see here that this is particularly segmented from the internal LAN for the security purposes, of course, also for performance purposes. So it only stretches out to public guest SSIDs. All right, so now that we understand what this network is doing, as we mentioned, we will be cutting off the top of this topology because we don't care about it for this talk. And we will be looking at just this inner portion of the network which carries user traffic around the network. So what would the result of the spanning tree calculation look like? It would look like this. As we mentioned, a root bridge is selected. In this case, our root bridge would actually be this core switch number 1 down here. So that's our root bridge, and all of the bridges or switches in this topology, you will see I use those words interchangeably, because a switch is really just a bridge where each port is an Ethernet port. For this purpose, doesn't again matter. Switch, bridge, the same for us. So this core switch is chosen as the root bridge, and all the other switches calculate the shortest path available in the network to that bridge and disable all of the other ports. So yes, we have a nice loop-free topology, and like we mentioned, we lost all our capacity at the cost of this loop-free topology. We still do have redundancy, because if any link fails in the topology, spanning tree will substitute a redundant link which is available, again with the shortest path to the root bridge, and turn that link on, unblock that particular link. All right, so that's nice, that works, but let's talk about why original spanning tree, like I mentioned, this protocol was designed in the early 90s, is not really for us anymore today. So it was quite slow. And this is one of the things that gave it a bad name in the networking industry. Yes, with the original spanning tree, up to 30 seconds could pass before a port, when you connect a new port, it would go up and start forwarding traffic, which in today's standards, that's ages, right? And also, the original spanning tree was not ever designed and ready for multi-gigabit links, so it really struggles with proper path selection in modern networks when we have, 10, 2500 gig links. So please do not use the original early 90s spanning tree in your network anymore today. Not a good idea at best, and it will not work properly at all at worst. All right, so of course, we have a better version of spanning tree, which is called RSTP, Rapid Spanning Tree Protocol. And Rapid Spanning Tree Protocol improves on STP by reducing convergence time quite massively, by introducing 2 new port states and 4 new port rows. We don't have to care about what these states and rows really are. We just know, the protocol implementation changed, and now it's much faster. So in a converged RSTP network, port transition time is usually measured in milliseconds. So as soon as a link is lost, a redundant link can start forwarding traffic in literally milliseconds. And another big advantage is that due to the new port rows that we mentioned, RSTP introduced the concept of edge ports, where we connect our edge and user devices, and these transition to forwarding immediately as they are connected, meaning that we can still utilize spanning tree and have no penalty to end users, even when using spanning tree. Because with the previous implementation of the spanning tree, a user would connect to the network and they would have a 30-second learning time before they can start using the network. Not with rapid spanning tree when properly configured, which is a big advantage. So yeah, RSTP is great and you should be using it. So every single one of your networks should be using rapid spanning tree at least. Every single one of my networks is. Why? I don't think it's acceptable that a single wrongly connected cable can bring down an entire network. And without any loop prevention method, that will actually happen. I've seen many, many networks where a non-technical user connects a cable and then doesn't realize it's the same cable and connects it to a socket nearby, and then boom, the network is down. So you should be using spanning tree of some sort in your networks, but using it doesn't mean just turn it on. It means it should also be properly configured. And most issues with spanning tree, and I really feel why spanning tree has a bad name or a bad reputation in the networking industry, is because people just turn it on and don't configure it at all. And that's not how it works. If you are deploying OSPF, you are configuring it with a particular intent in mind. You want to achieve some kind of topology. It's the same with spanning tree. You should be deploying it with understanding of how it works and with a particular goal, with a particular topology in mind. And so more on what is this proper STP configuration we will look at a little bit later in later slides. But you really should be using RSTP pretty much everywhere. All right, so what are the downsides of RSTP? Well, it is fast to converge, and it doesn't penalize end users for using it in your architecture, so that's great. And it can deal with fast modern links with multi-gigabit up to 100 gigabit links. That's also great. However, with RSTP, we still get the downside of disabling redundant links, which leads to inefficient link or traffic utilization in the network. And usually it comes down to, man, I have all of these links, so why should they be idle, right? Isn't there a better way to do it? And luckily, yes, there is MSTP, which is the purpose of this talk. And MSTP was developed exactly to address the limitations of the older STP protocols. So it introduces the concepts of regions and instances. And this way, MSTP can actually divide the network into multiple regions, and each region can have its spanning tree. By using this, MSTP actually allows us to use these redundant paths we have within each region in a separate spanning tree instance, which allows us to utilize all of the links in our topology properly. So great. How do we achieve this then? Or what was the issue even before, right? Because those are two separate issues that we want to look at. So first issue was, and this is why I mentioned that we can divide the network into multiple regions. Why is that helpful? Well, the first issue in this topology is that if you look at it, the server here down in hypervisor 1 actually has to go all the way up to the root bridge and down the entire stack of the network, so to speak, to reach hypervisor 2. That's quite inefficient. If you remember, there was a link right here connecting these server access switches. So why was it not used? Well, because it wasn't the shortest path for any network topology, so spanning tree just disabled it. Not great. Right, so we would want to solve that somehow. And the regions that I mentioned in MSTP allow us to solve that problem. And then we have the second problem of having these redundant links, which, sure, they fulfill their functionality of being redundant, and therefore there is if there is an outage or an unplugged port, those servers would still be reachable. But again, man, we have all of this capacity. Why not use it? We could double our network speeds if we only were able to somehow utilize those ports. And so in this particular case, the other function of MSTP, which we mentioned, so one is regions and the other is instances. So the instances will allow us to utilize those ports. All right, so let's look at how regions work first. So first, let's solve the problem of I have a link between these server switches. So this link is actually right here. So how can I change the topology of the spanning tree in this network to utilize that link for cross-server connectivity? So let's look at that. You go away. There we go. So regions allow us to carve out a part of the network, and that part of the network will have its own spanning tree. So each region has its own root bridge, and therefore its own internal spanning tree topology. So as an example, let's carve out this network that we have into multiple regions. So this is the original network. We see there is a bunch of stuff available. So what are our options? How can we utilize this regioning of the network? Well, let's section off the first cluster of servers into its own region. So if we do that, inside of that region, we can tell spanning tree that this server switch is the new root bridge, and all the links should point to it. All right, so here we see we've sectioned these bridges, these switches into a separate region, and calculated spanning tree on them. Great. Next, let's section off the second server cluster into a second region, and spanning tree calculates the resulting topology as we see here. Then the rest of the network will be in the third or a third region, and then of course spanning tree would calculate the topology on that as well. So that's an example. Okay, so how do those other regions that we just carved out, how do they interact with the rest of the network, the rest of the topology? Well, that's quite simple. Regions actually appear as edge bridges, as a single bridge to other regions. So each internal topology of each region is actually hidden from other regions. And we can basically visualize it like this. So we have this big main topology, which we can see here, that has calculated its topology to look like this. So this is our primary region. And then we have the second region here hidden as a single bridge, and the third region here hidden as a single bridge. Again, this particular topology does not see the internal topology of these regions. All right. So not great, but not terrible. So this particular topology that we have just chosen doesn't actually solve our problem. If you remember, the original problem was how do we keep the traffic between the server clusters flowing through the connection between those switches. And here we actually haven't solved that problem because the transit, to transit from cluster to cluster, the traffic still has to go through the main bridge of the main network. So yeah, this topology sectioning or regioning that we chose wasn't quite great. So let's fix that. So what if we move both the clusters into their separate regions? So here you see the clusters separated out with their own topologies. And now if we construct a spanning tree region like this and enable spanning tree on it, what will happen is that that region will look like a single big bridge from the point of the other topology. We can visualize it like this. It has 4 links to the bridge. Why? Because when we look at the original topology, which is somewhere here, you can see that we have 2 links here and 2 links here. All right? So from the point of view of the main topology, this will become a single bridge. And let's look how the internal topology of that region looks like now. It looks like this. And so there is an assumption here that we have chosen either this switch or this switch to be the root bridge of this region. But if we do that, suddenly we see that traffic from hypervisor 4 going to hypervisor 1 can take a much more direct path. So we are shaping the topology of the network by adjusting which bridges, which switches take part in which STP region. All right, so great. We have solved a traffic routing problem. And also, of course, from the point of the main region, it will cut off the redundant links to the other region as well. So we can visualize the connection between the server cluster region and the main region like this. All right, so great success. Communication between servers now takes the shortest path rather than going through the upstream network. So we have solved that problem. And here we can see how regions basically allow us to design topologies with flexibility. And this gives us power to enforce traffic routing, to do traffic engineering according to our needs, even when using spanning tree. So what you just saw in this example is that when implementing multiple spanning tree and when cutting up your network into regions, there is actual design topology involved. You have to decide what output or what result you want to achieve with sectioning of your network, and then think about and calculate how those resulting internal spanning trees of each region will look like. So it's not something that's automatic. It's a good analog to this would be areas in OSPF. If you are working with big OSPF networks, you are considering whether to implement areas or not, because there are also some traffic patterns in areas as well. So in OSPF, traffic between areas has to go through the backbone area, right? That's one consideration. Unless using virtual links, you can use virtual links, sure. But that is one consideration you might consider when designing a network with multiple OSPF areas. It's the same here in MSTP, in multiple spanning tree protocol. You have to actively decide what do you want to achieve, what are the desired resultant topologies, and how to achieve them using the tools available in the protocol. All right, so by using this or by doing this design exercise, we have now solved our issue with the servers. But we still have an issue of a bunch of links not really being utilized. Like, wouldn't it be nice if we could actually use the spare throughput that we have available here? So, you know, if we look at the original links, we do actually have a bunch of other links here which are still being unutilized. So how do we achieve that? So let's move forward with the other function of the spanning of the MSTP protocol that we mentioned. One was regions, and the other was instances. So in each spanning tree region, there can be one or more VLANs, and this allows us to carve out each individual VLAN to have its own spanning tree. And you can freely assign a single or multiple VLANs into spanning tree instances, MSTIs. So what this means is that when you have multiple VLANs, the traffic within each VLAN can take a different path, can have its own internal topology, which is different for an internal topology in the other spanning tree instance, spanning tree topology. And this allows us for each VLAN to define a different resultant topology, and therefore forcing traffic to take different paths for different VLAN, which is great because now we can actually load balance the traffic of different VLANs across all of the available links in our network. So here is a nice visualization how that would look like. So we see here that we have 4 VLANs inside of this particular server cluster or 2 server clusters. We have a VLAN for VM traffic within one cluster and storage traffic within another cluster, and we have a VLAN traffic and storage traffic within the other cluster as well. So I didn't want to break this down into 4 separate topologies, but I colored it here for you. And you can imagine this. So if there is storage traffic, which storage will be VMs accessing their storage, especially if we are using a hyper-converged infrastructure, storage will be a large part of your traffic utilization. And we can see here that storage would take these paths. On the other part, we have normal server traffic coming from users, and that would take these paths. And these are completely separate links, so now we are actually utilizing the throughput available on those redundant links, and we aren't slowing the user traffic by storage traffic and vice versa. So this way we do actually achieve load balancing and utilization of these redundant links by using multiple spanning tree instances. And of course there is still redundancy, because if anything breaks, you can picture this as 4 completely separate spanning trees inside of this network, one for each individual VLAN. But, of course, each spanning tree still has all links available to be used if needed. It's just each spanning tree instance eliminates or blocks different paths within that spanning tree instance. I do hope that makes sense. All right. So now let's look at the rest of our topology. We mentioned that we still have redundant links here as well, so let's use them as well. As I mentioned, this was a hospital network, so there was a general internal LAN, and there was also a guest Wi-Fi. So why not separate the guest Wi-Fi to go over different links than the internal LAN traffic? And definitely we can, so we just create a spanning tree instance for the internal LAN and create a spanning tree instance for the guest Wi-Fi, and we set different root bridges for each of those topologies. And then the resultant topology looks like this, again colored across the different links available in this topology. All right, so how would we achieve this, right? Well, if you think about it, we mentioned that all bridges calculate their path to the root bridge. So what actually happens here is that inside of this cluster VLAN, the purple one, this one, for the purple one, we set this switch as the root bridge. That works. All right, for the yellow one, we actually set this bridge as the root bridge. Then for the red one, do I have red? Maybe not. For the red one, we would set, maybe I do. We would set this bridge as the root bridge, etc. And by varying which internal spanning tree topology uses which bridge as its root bridge, we can achieve different topologies for each spanning tree instance. Same with here, again, like with the previous example. For the internal, the green LAN, we would set this switch as the root bridge. For the yellow, for the guest Wi-Fi, we would set this bridge as the root bridge. And suddenly, the internal topologies would be different, and the traffic routing in air quotes, because this is layer 2, would be different for each of those VLANs. All right, so now that we know all of that, let's get into some acronyms. And usually when people talk about spanning tree, they start the conversation with these acronyms. And for me, when I was originally learning MSTP, this was very, very confusing because you have all of these things like MSTI, IST, CST, CIST. Like, what is all of this? Well, I hope I can explain these terms better now that we have seen what spanning tree does to topologies visually. So we have MSTI, which is just a multiple spanning tree instance. It's just one spanning tree topology, and that can be a single region, or it can be a VLAN-based instance within a region, etc., etc. Then we have IST, which is the internal spanning tree, and each region maintains a single internal spanning tree. And for example, a region that doesn't have any VLAN-based instances only has the IST, the internal spanning tree instance. It's still an instance of the spanning tree. Then we have the CST, which is a common spanning tree, and the common spanning tree only contains regions and their interconnections. If you remember back to the slides, we looked at how we could visualize those other regions connecting to the main region as a single bridge. Well, the CST only maintains a topology of regions. So why is this useful? It's because MSTP is backwards compatible with older spanning tree protocols. And how this actually works, that if a rapid spanning tree, or the original old spanning tree bridge connects to the topology, it's only served the CST, the common spanning tree. And again, it's just another instance. So if a RSTP bridge connects, it only sees the regions as individual bridges. That's how backwards compatibility is achieved. All right, so how do we actually configure all of this? Let's look at proper spanning tree configuration on MikroTik now that we have done our design exercises and decided on how we want to configure things. All right, so first, there is the bridge setup. So in bridge setup, it's fairly simple. We are just creating a new bridge. And in the STP tab, we select the protocol we want to use. In that case, that would be multiple spanning tree. We then have the priority. And the priority decides how the root bridge would be selected. The important note here that this is the priority for the IST. If you remember about our acronyms, the IST is the base region of the, is the base spanning tree of the region. So this priority doesn't actually influence VLAN-based instances. It's just the base region that this priority influences the selection of the root bridge in. So we then have path cost mode. And here in path cost mode, there is a long and there is a short. We will talk about this on the next slide. One important note here is that MSTP requires VLAN filtering to be turned on. So please make sure VLANs are properly configured and VLAN filtering is properly configured. It's out of scope of this talk, but if you don't configure that properly, none of this will work. If you are interested in that, I'm sure you can find presentations and guides on the MikroTik wiki about all of that. All right, so we mentioned this path cost mode. What is that? How does that work? Well, path cost selects what values are used for link costs during the calculation of the shortest link to the root bridge. And here we have two options. We have the short and long option. Some vendors call this legacy and new. Some vendors call this STP versus RSTP. Each vendor has different names for this. What really matters here is that the short is the original from the early 90s spanning tree costs. And so always use long, because as you can see here, using the short, spanning tree cannot actually differentiate between a 25, 40, 50 gigabit link. It just doesn't understand what the difference is. So we always want to do long, but there is a big catch here. You want to make 100% sure that the path selection costs are the same across your entire network. Very important, particularly in multi-vendor networks. So be mindful of this. This has bitten me in the behind quite a few times. All right. So we've looked at bridge setup, fairly simple. We just select or tell MikroTik to use MSTP and set our priority within the main regional IST. And of course, if we want to use regioning, we need to configure the region name and the region revision here. This is very important. If you want to use regions, this needs to be configured, and each region would have its own name. And all the bridges within a region must have the same region revision to be counted inside of that region. There is a whole complicated algorithm how it works if these things are different, which you can read on MikroTik Wiki. I won't go into it here. In a properly configured network, this shouldn't diverge. So be mindful and careful about that as well. All right, so now that we have our bridge configured, it's set up for MSTP. We have the proper path cost protocol selected. We will be adding ports into our bridge. So let's look at STP settings within the bridge port menu. All right, and so here we have priority, which we don't really care about. In all of my years of networking, I think I've changed priority maybe like 3 times. So not really much reason to adjust it. Again, you can read up on the internal details of the spanning tree implementation on what it does. What is important here is path cost. So you can see here that these path costs are not configured, they are unconfigured. And what this means is that they are automatically established from the link speed negotiated on this link. There is a gotcha, there is a trick here that this is also documented on the MikroTik Wiki. If you are using LAGs, link aggregation groups or bonds within MikroTik, LACP, link aggregation control protocol, it will not actually calculate the link cost based of the sum of all the available links. So if you are using bonds, you have to configure path cost here manually. It's documented in the wiki. It's just how MikroTik works. All right. And then we have some security settings in here, a bunch of security settings. So we have the edge port, we have the isolation, we have some restrictions and BPDU guard. Let's talk about these. So what these actually influence is they are for security purposes, and they allow us to use this edge port concept that we talk about. When an end user station, a computer connects to a switch, it is instantly online. It doesn't have to go through the normal learning period of the port, which normally happens when you bring up a spanning tree port, which is great for end station. So there is the edge there. That's what it does. It allows a port to immediately go to a forwarding state, skipping the learning process, therefore bringing the end node online immediately, which is great for end station. Then there is the auto isolation. So what the auto isolation does is, it's the other hand. It will actually isolate a port until spanning tree is fully negotiated on it. So this one you don't want to turn on end node ports, only on infrastructure ports. Then there are some restrictions and a BPDU guard. You can read up on what these security settings do, again, on the MikroTik Wiki, but for your convenience, I have a very good recommendation here. So for ports to other spanning tree bridges, you configure settings like this. And for end device port, you configure settings like this. This way, you get security, you get fast convergence of the spanning tree, endpoints are immediately online, and at the same time, you keep all of the benefits of spanning tree. All right. So there is one last screen which we have here, which is MSTIs. Remember, these are those multiple spanning tree instances. So this is how we would define an instance within a region. You select the bridge, you give the instance an identifier, you give the priority this switch should take as during the root bridge selection process within this instance, and you map which VLANs should take part in this particular spanning tree instance. And then there are overrides, which allow us to override the priority for a port and the internal path cost for a port. I have personally never used this, but if you ever need it for some reason, it is there. So normally, ports inherit their properties from the property set in the bridge port menu. They inherit those properties for all spanning tree instances they are the part of. Here, you can, if you would like to override some of those properties for some spanning tree instances. All right, so we mentioned that we have this topology where we wanted to achieve both load balancing and redundancy and everything else within this particular spanning tree region. So how would we configure that on our MikroTiks? Well, it's actually quite simple. It's just a few lines of code. Now that we know what we want to do, it's just a question of how do we apply that to our MikroTik? Well, we create a bridge, and you will notice that we set priority of this bridge to become a root bridge of this topology in the IST. The default is 8,000, so 6,000 is lower. It will become the root bridge. We set our protocol mode to spanning tree. We set it to be a part of our region, and we turn on VLAN filtering, all good. Then we add a couple of ports into that bridge, and you see this auto-isolate edge, blah, blah, blah. All of that is turned on according to the recommendations that I mentioned on the previous page. And then we define our spanning tree instances, right? So here we just say that within this particular VLAN-based instance, I should be a root bridge within 201, and I should have a lower priority within 202. So this allows us to select that within VLAN 201, I will be the root bridge, and within VLAN 202, somebody else can become the root bridge, and therefore the topology will be different. And so this allows us to create this entire setup that we have here. All right, and that's really it. Like I mentioned, the configuration is not hard. It's just the understanding of the mechanisms or mechanics of the internal workings of spanning tree. So as soon as you understand that, as soon as you do these design exercises and decide on what the resultant topology should be, applying that intent to the configuration is actually not hard. It's just a few lines of code. All right, so tips and tricks. Like I mentioned during the talk, please make sure the path cost model is the same in your entire network. Like I mentioned, in multi-vendor networks, this can be a mess because some vendors can use a different path cost for different links and you won't even know it. Some vendors let you configure this and each vendor calls it differently, so just make sure it's the same. Study the documentation of each vendor. If you are MikroTik only, that's easy. Set path costs properly on bonds, on tunnels, and on all interfaces which don't natively expose their path costs. So that's a gotcha that you have to be careful about. And another tip and trick is monitor the topology. Monitor who the root bridge is, because you should be setting explicitly who the root bridge is, because that is what defines the topology, right? So you want to be quite sure that when a root bridge becomes something that you are not expecting to become a root bridge, you should know, and your monitoring system should notify you of that. And then finally, validate if the configuration works as expected. So we did our design, we have some particular resultant topology in mind. We should validate if we get the topology functional after we configure spanning tree. And beware of bugs. And I don't mean just MikroTik. I've seen some crazy stuff from big boy vendors, from Cisco, Juniper, etc. Each vendor usually has a ton of bugs. I've got 40 seconds on the timer. One funny bug I saw is when you defined a link aggregation group, LACP, spanning tree would not consider it, and this was not on MikroTik, by the way, this was on another vendor, very expensive vendor. Spanning tree would not consider the bond group as a single link, and spanning tree would turn off links within the bond. Great, thank you. Yeah, we went all the way to Taiwan to developers with that one, and basically we returned like 50,000 euros worth of equipment because of that bug. So there are bugs in big boy vendors which you wouldn't expect, not just MikroTik everywhere. And that's it. Thank you very much for your time.